In section 5 of the course, we'll talk about Fourier frequency analysis. There will be two main topics. The first one is the Fourier series. It's the decomposition of a periodic function in sums of sines and cosines, okay? And then later on we'll see what we can do for functions which are aperiodic, and there we'll be able to use the Fourier transform. This Fourier transform will be related to the Laplace transform. In previous versions of the course, the Fourier series was obtained using projection arguments. This type of development can still be found in the slides that I have skipped, but my experience was that, well, students got lost during the presentation. Okay, so in this video course, I will use an analogy between the decomposition of a vector in the standard basis of our cube and the Fourier series, and hopefully this will be helpful. Well, let us first talk about the standard R-cube basis that is shown over here, and this should look familiar. You know that it's an orthonormal basis. Okay, so this means that these vectors over here, E1, E2, and 3, are perpendicular, and that each of these vectors have a unit length. In order to be able to talk about, well, perpendicularity, orthogonality, and length, you need a scalar product, sometimes called an inner product. Okay, in French, produit scalaire, and the scalar product of V and W is given over here, right? And you know that if V scalar product with W is equal to 0, then V is perpendicular to W, and you know also that the length of V, well, that's the scalar product of V with itself, and then you take the square root. Okay, so this is how you see that the basis here is orthonormal. If you take, well, EK scalar product with EL, and K and L are different, let's say for instance E1 and E2, if you take the scalar product, indeed it's 0. So E1 and E2 are, well, kind of perpendicular. Okay, and if you take K is equal to L, let's say K is equal to L is equal to 1, you can see that its length is indeed 1. So what you can do with this basis is that you can take any vector V and decompose it in the standard basis. This means that you write it as a linear combination of the vectors E1, E2, E3, right? And this can be written like this. And here you're going to say, well, why does he write C1, C2, C3? It's obvious that C1, C2, and C3 are, well, indeed, V1, V2, and V3, okay? So V can be written as V1 times E1 plus V2 times E2 plus V3 times E3. Okay, this is kind of obvious when you look at these vectors over here. This is the decomposition of V in the standard basis. But how are these C1 obtained? Well, you can see it as the let's compute, for instance, C1. It's the scalar product of V with the corresponding vector in the basis over here. Okay, and if you do that, V1, V2, V3, scalar product with 1, 0, 0, you indeed see that this is V1. Okay, so V can be decomposed in the standard R-cube basis as follows, and the coefficients here the coordinates C1, C2, C3 are simply obtained by taking the scalar product of the vector with the corresponding element in the base. So let us now go to the Fourier series, and at first look things will be completely different, but you will see that there are analogies with this standard R-cube basis, and I hope that this analogy will help you. So what we want to do is decompose a function that is periodic in a sum of sines and cosines. When you think of sines and cosines, well, you can kind of think of complex exponentials. Okay, remember that this one here can be written as the cosine of k omega 0 t plus j sine k omega 0 t, right? So it contains cosines and sines. So we'll be using this Fourier basis of complex exponentials. Okay, so here basis. Okay, remember for the basis there was this idea of perpendicularity, orthogonality. So we'll have something similar. There was also this idea of length, length 1, and we'll have something similar over here as well. So there is also another difference. Here in our basis we have an infinite number of functions in the basis. Here we had only 3. Okay, here k is an integer, so we have an infinite amount of functions in the basis. And there is another difference. Here we have vectors in the basis, and here it's a basis of, well, functions, complex exponential functions. Okay, so, well, there is an analogy, of course, but there are some differences. So to have a basis, or to qualify as a basis, we need, well, this idea of orthogonality and length 1, and to introduce these ideas you have to have a, well, as we had here a scalar product, we need also a scalar product, and in this case it's, well, more often called an inner product. Okay, so the inner product of two functions in the base, and it will be written differently also as well. Okay, it's not written as fk dot fl. Okay, this is not the right notation, but here you have the inner product of fk and fl, and it is defined like this. Okay, so where here this is the complex conjugates. So this is going to play the role of scalar products, just as here we had also a scalar product. We'll show in the next slide that the functions that are in the Fourier basis, well, they lead to an orthonormal basis, in the sense that if you take the inner product of a function with an index k and l, well, this leads to a 1 when k is equal to 1, and to a 0 when k is different to l. Okay, so this is an orthonormal basis of complex exponentials, and it's called the Fourier basis. So what we'll do using the Fourier basis is take our function here. Okay, it will be a periodic function, and we'll decompose it in the Fourier basis. This is exactly what we are done with our vector in R-cube. We had decomposed it in the standard R-cube basis. Okay, and this could be written like this. Well, this is equivalent to that. Okay, so this is exactly what we are going to do, right? And remains the question on how to compute this ck. So let's have a look how we did it in well, this decomposition of v in R cube? Well, you take the vector v and you take the scalar product with the corresponding vector in the basis. So if you want C2, you take the scalar product of v and E2. Well, this is exactly how we are going to proceed. Okay, CK, the Fourier coefficient, okay, will be computed as the inner product of f. Okay, f plays the role of v here with the corresponding element in the base. So fk plays the role of ek over here. And if we have a look at this inner product, well, it's this integral here. Okay, here we have f of t, and we have to take the complex conjugate of fk, and this leads to the minus sign over here. So this is how we are going to compute the Fourier coefficients that allow you to decompose f of t, a periodic function, in the Fourier basis. So let us come back to this complex Fourier basis that we had written like this. Okay, remember that it's cosine k omega 0 t plus j sine k omega 0 t, but we prefer to write it in this compact way. Omega 0 is the fundamental frequency. It's 2 pi over t, and t will be the period of the signal we are trying to decompose in this complex Fourier basis. Remember, k is an integer, 1, 2, minus 1, minus 2, etc. So there are an infinite number of functions, complex exponentials, in this Fourier basis, right? Remember, from the analogy with the standard R cube basis, we would like this basis to be orthonormal, and when you look at orthogonality and lengths, well, you needed a scalar product, and the scalar product of two functions in the family is given by this expression over here. This is the inner product of a function with index k and a function here with index l. And if this, well, Fourier basis is orthonormal, then if you take two functions, okay, with k different from l, you should have a 0, indicating that these, well, functions are kind of orthogonal to one another. And if you take k is equal to l, then you should have a 1. This is the same thing as with the standard basis in R cube. If you take the scalar product of E1 by itself, you have a 1, and if you take the scalar product of E1 and E2, you have a 0. Okay, so another way to write this is to say that it's 1 over t. Okay, remember that t is the period, and that you integrate over some period. It doesn't matter which period. This is indicated by this t0, which can be anything. You integrate from t0 to t0 plus t. So this is simply saying that you integrate over a period. Okay, so let's have a look at this expression. It's 1 over t, the integral over a period. This thing here is e to the j k omega 0 t, and this one here, you have to replace a k by l and take the complex conjugate, so you'll have e to the g l omega 0 t, but you have to put a minus sign because of this complex conjugate. Okay, so this you can rewrite as 1 over t, the integral over a period of e to the j, and now k minus l omega 0 t dt. Okay, so what happens if k is equal to l? Well, this is going to lead to the, and this is k equal to L, this is going to lead to 1 over t integral over a period. If k is equal to L, this will become a 1 over here. So you integrate 1. Okay, so this is going to be, well, this is going to be t, right? And so you indeed obtain a 1. Okay, and when k is different from L, well, then you have this expression over here. Okay, but when k is different from L, then you'll have sines and cosines. And if you know that if, for instance, you have a sine over here and you integrate it over a period, okay, let's start the period over here and let's end it over here. So this is t 0 plus t. Well, you'll have a surface under the curve which will be 0. This is the part of the curve that is above 0, and in here you'll have the part that is below 0, and if you add this, this will be 0. Okay, so integrating trigonometric signals over a period always leads to a 0. Okay, so when k is different from 0, this is going to lead to a 0. Okay, so this Fourier basis is indeed orthonormal when you consider the following inner product. Using this Fourier basis, you can obtain the Fourier series representation of a signal that is periodic of period t. Okay, and this Fourier series representation is an infinite sum of weighted complex exponentials. Okay, complex exponentials can be seen as a cosine and sines, right? And in this infinite sum, you have these complex exponential at different frequencies here, where omega 0 is the fundamental frequency, 2 pi over t, and you see that in this sum we have multiples of this fundamental frequency, and k omega 0 will be the kth harmonic of the fundamental frequency. In this sum appear the so-called Fourier coefficients. This is how the function is decomposed in the Fourier basis, and this can be seen as kind of coordinates in this Fourier basis, and these Fourier coefficients are computed as follows. And what you have over here is the inner product that has been used to show that the Fourier basis is orthonormal, right? This is kind of similar to what we have done in the case of decomposition of a vector in R cube. Well, there the ck is, well, the scalar product of the vector with the corresponding vector in the base. Well, here you have something similar. It's the inner product of f with the corresponding signal here in the basis. And if you look at this inner product, you can write it like this, where you have here the convex conjugate, and if you plug in the corresponding function in the basis, this is what you obtain. So this is how the ck is computed, and ck is a complex number, and it can be obtained by computing this interval over a period. So this is what we obtain in summary. Here you see the Fourier series representation. This is the function fk that is in the Fourier basis, and the ck are kind of the coordinates of f of t in this basis, and they are computed as follows. So remember that we had decomposed our function f of t as a sum over k right, of the ck e g k omega 0 t. And this is the Fourier series representation of f of t, and the Fourier series will converge to f of t for all values of t as long as the function is piecewise smooth. Okay, so there can be discontinuities, but in between discontinuities the function is smooth. Well, this means that the function is well behaved. The mathematician Dirichlet showed that this Fourier series converges, okay, if it meets, and the signal meets the following sufficient conditions of over a period. The function must be absolutely integrable. Okay, so since it's over a period, this means that the integral over one period of the absolute value of f of t dt must converge. So this is the main property, main condition, and there are two other rather technical conditions, because in practice signals will surely meet these two conditions. The function of t must have a finite number of maxima and minima and a finite number of discontinuities. So let us have a look at the convergence of the Fourier series representation at a point of discontinuity. So let us draw a function here of time with a discontinuity in t is equal to 0. So the function might look like this, and then suddenly at t equals t0, so I should put here a t in front. Well, there is a discontinuity. Okay, so you can kind of define two quantities over here. First start by this one. This is f of t0 minus. This is the value that takes the function if you approach t0 from the left, and it can be written by this limit. And if you approach t0 from the right and you take the limit of that function, this will be called f of t0 plus. Okay, and it can be written using this limit over here. Okay, so there is a discontinuity at t is equal to 0. Well, if you take the Fourier series representation, the Fourier series representation will kind of converge to this average value of these two quantities over here. So it will converge to this value over here. Okay, so if f of t is continuous elsewhere, of course the series converges absolutely and uniformly at all times t where the function is continuous. Okay, although this Fourier series converges to the average at discontinuities, there is a kind of a ringing effect before and after discontinuity points, and this is called the Gibbs phenomenon. Okay, so let's apply this to a periodic function of period t over here, and this function is 1 over half a period and minus 1 over the rest of the periods. Okay, so we need now to compute the Fourier coefficient. So remember first that we're trying to decompose f of t as a sum of complex exponentials, and the ck are the coordinates of f in this, well, sum of complex exponentials, and this is the function fk of t. It's a function in the Fourier basis, and we've seen that ck, well, it's the inner product of f of t with the corresponding function in the Fourier basis, and this could be written, and this because we had used or defined an inner product for our Fourier basis as 1 over t integral over the periods, any periods, of f of t, fk of t dt, and conjugate over here, and this leads to the following formula. So this integral from 0 over t, you can rewrite it as the sum of two integrals. The first one from 0 to t over 2, right? Because the function is 1 over there, and then for an integral from t over 2 to t, and there the function is minus 1. Okay, so now we need to integrate this function over here, and you've got it over here as well. So you obtain the same function, but you have to divide by minus, there it is, j2kp over t. Okay, j2kp, you have got it over here, and divided by t, well, we've brought it back to the numerator. Now we can evaluate at the integration bounds. This is what you've got for the first one, and this is what you got for this one over here. Okay, so e to the minus j2kp, right, if k is equal to 0, well, this is a 1, of course, but if we draw the unit circle, so this will be the real part, and this will be the imaginary part. So you're here, and if you turn, okay, by 2p, you end up at the same spot. Okay, and whatever the k over here, you always end up here in 1 over here. So this is a 1, and if you now simplify, and you'll have minus 1, so it's minus 2. You have two terms like this one over here, so this simplifies to this expression over here. If k is even, okay, this will produce again 1. Okay, so you have 1 minus 1, so you'll have a 0 over here. This is if k is even or 0, by the way. Okay, if k is odd, okay, you'll end up over here. Okay, so you'll have minus 1, minus 1, minus 1, 2 with a plus sign over here, and this one you could also rewrite it as minus j2 over kp. This would be another way to write things. Okay, what we've got here is the Fourier series representation. For the function that we have considered, we had already computed the Fourier coefficients ck. They are 0 for k even and 0, and they are given by this expression here when k is odd. Okay, so now what we can do is write all these terms over here. Okay, you have an infinite number of terms. You start from the negative integers and you go up to infinity. You notice here in the ck that there will always be a factor 2 over j pi, so you can put it in front and put two big parentheses, and then now you start to consider every k that is odd. Okay, so what you'll have here is k as the term corresponding to k is equal to minus 5. Here you'll have the term that corresponds to k is equal to minus 3, and here you'll have the term that corresponds to k is equal to minus 1. Here you'll have the term that corresponds to k is equal to 1. Here you'll have the term that corresponds to k is equal to 3, and here you'll have the term that corresponds to k is equal to 5. Okay, so in this sum you always have a positive integer, okay, 1, 3 and 5, and the corresponding term with the negative integer, corresponding integer. So what you can do is kind of work with positive integers that are odd, of course, because the even coefficients do not give a contribution, and write the corresponding term, okay, the positive integer, and let's say these ones, and these ones, they will have a plus sign, and the corresponding terms will have a minus sign. Okay, so for each odd positive integer you have terms like that appearing, and then you have to remember, and this is something that we have seen at the beginning of the course, and it results from Euler's identity. This you can write e to the gat minus e to the minus gat over 2j. Okay, so you can see that this is 2j times a sine. Okay, so the function can be decomposed as a sum over odd positive integers. Okay, so don't forget that you have to multiply by this one over here. Okay, so this one here needs to be multiplied by this one here. So this is how you end up with this coefficient times a sine. So you could rewrite this thing here as sine, okay, because omega 0 is 2 pi over t, so you can rewrite it as k omega 0 t, and omega 0 is the fundamental frequency. So we have decomposed our function, okay, as a sum of sines with, well, a certain coefficient here in front, and in this sine we have the fundamental frequency. This is k is equal to 1, and we'll have 3 times the fundamental frequency, 5 times the fundamental frequencies, and so on. Okay, so you see here that you have a sum of sines. Well, this is not a surprise because this is a function that is odd. Okay, so if you decompose it as a function of, well, in a Fourier series, you expect a sum of functions that are odd as well. And of course, sine functions are examples of odd functions. It would be kind of a surprise to see a cosine in a Fourier decomposition of a function that is odd. So we have decomposed our signal that is of period t as a sum of sines at k times the fundamental frequency, and here, well, k is odd, and in each term you have a coefficient that is in front of the sine, which is 4 over kp. So you see that the contributions of higher order fundamentals, okay, will decrease as you have a 1 over k relation in this term. So let's have a look at what happens after one term. So here in blue you have the original signal that we are decomposing in blue, and you have here the first term of the Fourier series. You can see that it corresponds to k is equal to 1, and indeed it has the same period as the original signal in blue, so it's at the fundamental frequency, and the amplitude is 4 over k pi. K is equal to 1, so this leads to an amplitude of 4 over pi, and this seems to be okay. So let us keep on adding terms. Here you have a term appearing at k is equal to 3, so the underlying sinusoid is at 3 times the fundamental frequency, and of course the amplitude has reduced because this is 4 over k pi with k is equal to 3, and if you add the two terms you obtain the curve in red full line, and it starts to approximate the blue line better and better. So here we have added the third term that corresponds to k is equal to 5. So the underlying sinusoid is at 5 times the fundamental frequency. The amplitude has been reduced again. Remember this relation in 1 over k. And if we add the 3 first terms, you obtain the full green line. So here we have added a fourth term that corresponds to k is equal to 7, and you see now the result after 4 terms is the red full line, and what you see is of course that the approximation improves, and this is what you have obtained at k is equal to 9. So we have now 5 terms in the Fourier series, and what you see is that the approximation gets better and better, and you see this ringing effect, this Gibbs phenomenon appearing. Notice also that the Fourier series always converges to the average of the function before and after the discontinuity. So in this case, well, the Fourier series at this discontinuity points converges to 0. So we can have a look in Google your best friend and type Gibbs phenomenon, and you arrive at this page, and it explains you that the phenomenon has been discovered by Mr. Gibbs, well, already quite a while ago. So what you see here on the right is the decomposition in Fourier series of the same function that we have considered in the slides, but what they do here is go further and add more and more harmonics. So this is how the Fourier series looks after 5 harmonics. Here 25 and 125 harmonics, and this is this ringing effect, this Gibbs phenomenon, and it's due to the fact that you're approximating a function that is discontinuous by a sum of functions that are continuous. So we have decomposed a function f of t of period t as a sum of, well, an infinite number of terms ck e to the jk omega 0 t, so a sum of complex exponentials, and in these complex exponentials, well, you have sines and cosines. Okay, so this is f of t, and what you can then do is, well, take this Fourier coefficient, it's a complex number, and of course you can consider the modulus, and you can consider the argument of ck, and you can represent that in a plot as a function of, well, k. In fact, it's k omega 0, and this gives you the magnitude line spectrum and the phase line spectrum. Okay, this one will leave aside, and we'll see, well, what is the interpretation of these two spectra. So let's have a look at these spectra in the case that we've considered in the course, and this function that was periodic and switching between 1 and -1. Remember that ck is equal to 2 over jk pi for k odd, and we had ck is equal to 0 for k even. Okay, so we can have a look at now the modulus of ck, and that's 2 over the absolute value of k pi, okay, for k odd, and we can have a look at the argument of ck. Well, that will depend on the sign of k. Remember that 1 over j is equal to minus j. So if k is positive, we'll have minus j. So the argument will be minus pi over 2. This is k positive and odd. And it will be pi over 2 when k is negative and odd. And here it's k even or 0, right? So here it's nice and easy. Modulus of ck is 0, and the argument of ck is 0 as well. And this is precisely what you see in the magnitude and phase line spectra. Now you see here that when k is even and so on, or 0, this is the case here also, we see zeros. And when k is odd, okay, we see this dependence in 1 over k in the magnitude line spectrum, and we see indeed minus pi over 2 for k odd and positive, and pi over 2 for k negative. Okay, and we'll come back to this slide here, or to the interpretation later on in the course. So this is the Fourier series representation of a function that is periodic in t, right? And ck was the inner product of ft e with e to the minus jk omega 0 t, and this is fk conjugate, and so this is 1 over t, the integral over one period of f of t e to the minus jk omega 0 t dt, right? This is ck over here. So what we do over here is decompose this sum in, well, 3 terms, one corresponding to k is equal to 0, and then this sum we decompose in the sum from minus infinity to minus 1, and from k equals 1 to infinity. This one we can rewrite it differently. We can write it as k is equal to 1 to infinity. We have to change the sign of k, and it will be c of minus k e to the minus jk omega 0 t. Okay, so now we have a sum from 1 to infinity here and 1 to infinity there, so we can write this as one sum from 1 to infinity, and this one we find it over here, and this one here we'll find it over there. Okay, and the advantage is now that we have a sum over positive integers. C0, if you look at this, C0 is equal to 1 over t integral over one period. If we put a 0 over here, it will simply be the integral of ft dt. Okay, so we integrate the function over one period and we multiply by 1 over t, and this will be simply the average value of f of t. So in the previous slide we have rewritten the Fourier series representation as follows. So it's C0 plus a sum that goes from 1 to infinity of an expression, and this expression is the one that you see over here. So you have to plug it in over here, and each k corresponds to a frequency that is k omega 0. Okay, so the term that you've got here, and we had already seen that it's the average value of f of t, corresponds to a signal at a zero frequency. This is why we call it, well, the DC component or the average component of f of t. And then you have, of course, terms in this sum that will correspond to, well, the kth harmonic of the fundamental frequency, k times omega 0, and this why a term in here in this sum with a k that is larger than 1 will be called the kth harmonic component of f of t. If k is equal to 1, then it's in the decomposition the term that corresponds to the fundamental frequency, so this term will be called the fundamental component of f of t. So far we have considered a function f of t that could be potentially complex valued, but in practice, in most applications, we'll use a function that is periodic, of course, but also real valued, and you will see that there will be some simplifications. Okay, so this function f of t that is real valued can be represented in the frequency domain by the Fourier coefficients. They are complex numbers, remember, and a complex number you can always write it under polar form, and these Fourier coefficient ck here, well, it represents, well, the contribution of the complex exponential at the harmonic frequencies k times the fundamental. Okay, we have seen that ck can be written as the inner product of f of t and the corresponding Fourier function in the basis, and we have seen that it can be written like this. Okay, so this is c of k. So let us now look at c of k, and let us assume that we take the complex conjugate of ck, and remember that the function f of t is real valued. So in this equation over here we see that f of t is real valued, so if we take the complex conjugate, the only thing that is going to change is that this one will become a plus over here. Okay, so ck conjugate is equal to, if we change the sign, well, it's changing the sign of k, so this is equal to c of minus k, right? And this c of minus k, it can also be written under, well, polar form. Here we have the polar form of the complex number c of minus k, but since c of minus k is equal to ck conjugate, we can take the conjugate of this one over here and we obtain this thing over here. So now we have that these two here are equal. Okay, so what do we see? Obviously the two modulus must be exactly the same, so we have that the modulus of ck is equal to the modulo of c minus k, but this means that the magnitude line spectrum is even, and we see here that the argument of c minus k is equal to minus the argument of ck. So we have this relation over here, and this means that the phase line spectrum is odd. Well, of course, if we know that our signal is real valued, and in, well, most applications, if not all, it will be the case, well, we only have to consider these two spectra when k is larger or equal to 0, because we can reconstruct the magnitude spectrum using a symmetry around the vertical axis, and the phase line spectrum using a symmetry around the origin. So these were the two spectra in the case of our example of the function that is switching between 1 and -1. We do indeed see that the magnitude line spectrum is even and that the phase line spectrum is uneven. So we only need to consider the part of the spectrum when k is larger or equal to 0, right? This is because the function that we've taken in our example is real valued. So this is what we obtain when we only consider the magnitude and phase line spectra for k positive or 0. So let us consider again a function that is real valued and periodic of periodic t. So we can find its Fourier series representation. You can take this complex number and write it in polar form. Okay, remember that this is what you find in the magnitude line spectrum, and this is what you see in the phase line spectrum, because now I'm going to give you the interpretation of these two spectra. So you can rewrite this, and by taking these two together to this expression over here. Okay, and here we have a sum, so we can decompose it as something that is C0 plus a sum that goes from -infinity to -1 plus a sum that goes from 1 to infinity. Okay, this one we can also rewrite as a sum from 1 to infinity by changing variables k to -k, and if you do that you arrive at this expression over here, right? This is equal to the modulus of ck, and this is equal to minus the argument of ck. This is because the function is real valued, so you know that the magnitude line spectrum is even and the phase line spectrum is uneven. Okay, so we arrive at this expression, and this is a cosine that is multiplied by 2, so it's maybe easier if we take the 2 inside the sum. And this is one way of rewriting the function f of t that is periodic when it's real valued. So let us come back to our example, and this example of this periodic function switching between 1 and -1, and see now if we can use this magnitude line and phase line spectra to kind of understand what is happening. So remember that we had decomposed f of t as a sum of, well, positive but odd terms that involve 4 over k pi the sine of k omega 0 t. So omega 0 was 2 pi over t. So we have decomposed the function in a sum of sines at the fundamental k equals 1 and harmonics k larger than 1, and well, the amplitude of each term is given by this coefficient over here. So in the previous slide we had written f of t is equal to C0. Okay, that's the average value. In our case, well, the signal is such that on one period 50% of the time it's 1 and the remaining 50% it's -1. So in our case this will be 0. You can read it also on the magnitude line spectrum. At k equals 0 we have indeed something that is consistent. And we had a sum, k is equal to 1 and it goes to infinity of 2 times the modulus of ck, and the modulus of ck, it can be found in the magnitude line spectrum, times a cosine of k omega 0 t plus the argument of ck. Okay, and the argument of ck, it can be written or read in the phase line spectrum. Okay, so we see here in these spectra that when k is even there is no contribution, and indeed this is consistent with what we see over here. We see in these spectra that when k is uneven, well, we read in the phase line spectrum that, well, the argument is minus pi over 2, and if we put minus pi over 2 in here, okay, then the cosine becomes a sine, okay, and this is indeed what we see over here. Okay, so the meaning is, if you look at the phase line spectrum, well, is it a sine or is it a cosine? Okay, if you have a phase shift of minus pi over 2, since you write it like here in the decomposition as a sum of cosines, you know that in reality it's a sum of sines. So this is the interpretation of the phase line spectrum. And when k is uneven, you can have, well, the amplitude of the relevant signal, sine or cosine, that will depend on the phase line spectrum, as I said, by simply going to the magnitude line spectrum and take the corresponding, well, k and multiply by 2 over here. Remember that ck was equal to 2 over jk pi, so the modulus of ck, and this one can be read over here, is 2 over k pi. Okay, indeed 2 modulus of ck is indeed what you read over here. So in here, in this magnitude line spectra, you take the corresponding k. If k is equal to 1, it will correspond to the fundamental, and when k is different from 1, well, you have the harmonics, and you can read if, well, in the decomposition of ft, is it a sine or a cosine? This you can read in the phase line spectrum. In this case here we have a phase shift of minus pi over 2, so we know that it's a sine, at least if k is odd, otherwise there is no contribution. And you can read the magnitude in the magnitude line spectrum. You take the corresponding k and you have to multiply by 2 to have the correct amplitude. So in the previous slide we had written f of t as, well, c0 plus a sum where k goes from 1 to infinity of 2 ck cosine of k omega 0 t plus the argument of ck. Okay, so this sum corresponds to terms in k, okay, and k is equal to 0, well, corresponds to this average component. It also corresponds to the zero frequency, and sometimes in English it's called the DC component, right? If we take the term over there with k is equal to 1, it corresponds to the fundamental frequency omega 0, and the equivalent term, this one over here, will be denoted as the fundamental component of f of t. And then for k larger than 1, we have the frequencies k omega 0, and they're called the kth harmonic of the fundamental frequency, and therefore the corresponding terms that are over here are called the kth harmonic component of f of t. Let us come back to our example of this square signal switching between 1 and -1. If we take the term in here that corresponds to k is equal to 1, we have 4 over pi sine 2 pi t over the period, and this is the fundamental component of f of t. And if we now take terms that are larger than 1 and that are odd also, we have 4 over k pi sine of 2 pi k t over the period, and this is called the kth harmonic component. And again, here we assume that k is larger than 1 and odd. So in what follows, what we want to do is, well, kind of have some properties for the Fourier series of an even function of an odd function. So this will involve finding the Fourier series of the time reflected version of a function. So assume that we have the Fourier series representation of a function f of t of period t. Here it is. And we know how to compute the ck, right? This is by this equation over here. So far we have nothing new. Well, now what we would like is the Fourier series of the reflected function f of minus t. So what we can do in this expression over here is replace t by minus t, and this is what you obtain. Okay, but in this expression, if you replace k by minus k, well, you just changing the ordering in the sum, but you will not change the sum itself. Okay, so if you do this, you obtain this expression here for f of minus t. And the reason why we do this is that because here we recognize f of k. So this is the Fourier function in the basis, and this last expression is indeed a Fourier series. Okay, so you can obtain the Fourier series for the reflected function from the original function by simply reflecting the Fourier coefficients. So what we can do now is use the preceding result to have a look at the Fourier series of a real valued even function and a real valued odd function in the next slide. So we know that if the function is a real valued, then ck is going to be c minus k conjugate. Okay, so we know also that if f of t has Fourier coefficients ck, the Fourier coefficients of the time reflected function will be the reflected Fourier coefficients. Okay, if the function is even, we know that these two here are equal, so this means that these two become equal as well. So we now have this relation over here, and this means that ck is equal to its complex conjugate. So if you have a complex number a plus bj, its complex conjugate is a minus bj, and if these two are equal, this means that they are equal to a, right? That the imaginary part must be 0. So in the case of real valued even functions, the Fourier coefficients are real. So remember that f of t is, well, a sum from minus infinity to infinity of ck ej k omega 0 t. So you can decompose it in a sum with c0, then a sum that goes from minus infinity to 1, and a sum that goes from 1 to infinity. This you can then rewrite by, well, changing k by minus k into a sum from 1 to infinity, and then you can collect all terms in this sum from 1 to infinity. This is what has been done over here. We have done something similar previously, and what we have now, since, well, the function is even, we have that this is equal to ck. We can put the ck in front, and this is what we obtain over here. This is Euler's identity, so this is 2 times this cosine over here. So we've just shown that if the function is real valued and even, it can be written as, well, an average component plus a sum of cosines. Well, this was to be expected because the function is even, so you expect a sum of cosines, as cosines are also even. It would be kind of weird to have a sign in the sum. So you can do something quite similar when the function is real valued and odd. Okay, so f of t is, well, characterized by Fourier coefficient ck. The reflected function f of minus t will have Fourier coefficients f minus k, but this time f of t is equal to f of minus t, right? So we get this expression here, and we see that ck is equal to minus the complex conjugate of ck. So if ck is a complex number a plus bj, its complex conjugate with a minus will be minus a plus bj, right? And if these two are equal, this means that this is equal to bj, so that the real part is 0, and now the Fourier coefficients are purely imaginary. Okay, so we can do this trick again, except that if the function is odd, you will always have c0 is 0. Okay, this is because of the property that the function is odd. So it's not that I forgot to put it over here, it's simply 0, and you'll have otherwise the same sum, and this one now is minus ck. So we can put the ck in front, and we have again that we can use, well, the consequence of the Euler identity, and this is 2j times a sine. Okay, since ck is purely imaginary and you multiply it by j, well, 2j ck will actually be a real number. So we have decomposed a real valued odd function in a sum of sines at the fundamental and the harmonics. This is not a surprise because we expect that if we decompose an odd function, we find sines, because sines are odd functions. And again, it would be weird to have a cosine in the sum, because a cosine is an even function. So the computation of the Fourier coefficients require some attention, it's complicated, and what we propose here is a method based on the Laplace transform. So remember that ck is computed as follows: 1 over t integral over a period of the function times the Fourier function that is complex conjugate, so it's e to the minus jk omega 0 t dt, and the Laplace transform, if we take the two-sided Laplace transform, is the integral from minus infinity to infinity of f of t e to the minus st dt. So there are some differences. We notice a gain over here of 1 over t, and here the gain is 1, so that's quite easy to solve. We see that the integral is over one period here, and here is from minus infinity to infinity. And then finally we see here we have s, and here we have jk omega 0 t. Right, so how can we use the Laplace transform to compute the Fourier coefficients? Well, let us first draw a function f of t that is periodic. Here's an example. I'll draw it as periodic as possible. It's not easy. Okay. So let us take a period here, t0, and here t0 plus t. To compute the Fourier coefficients, we need to consider one period, and if we take the Laplace transform of this function, well, we'll end up with integration bounds from minus infinity to infinity. So what we might do is use a rectangular window that is 1 inside, well, the period that we've considered, from t0 to t0 plus t, and that is 0 outside. So if we do the multiplication of f of t with this window, what we'll do is obtain the function, okay, that looks like this. And we'll call this a function f of t restricted to one period. Okay, so if we take the Laplace transform of this one, this thing over here, then we'll do an integration from minus infinity to infinity, but since the function is 0 everywhere except in the interval from t0 to t0 plus t, we'll have an integral that will correspond to what we want in the computation of the Fourier coefficients. Okay, so what we'll do is construct the function that is shown here in red. It's the restriction of the initial function over a period, and you can obtain it by multiplying f of t using a window, and we've seen previously that this window can be constructed from two steps. Once you have this restriction, what you can do is compute its Laplace transform, and then you need to take into account that you have to multiply by 1 over t, okay, and in the end you need to replace s by jk omega 0, and in this way you can obtain the Fourier coefficients using the Laplace transform. So let us use this way of computing the Fourier coefficients to our example of a square wave switching between 1 and -1. And remember that we have to construct this restriction of the initial function f of t to one period, and here we'll stick to one period, and we'll make it nice and easy. We'll take a period, well, between 0 and t. So this is the function that we're considering. So and here it is, and it is this function over here. And this function, we've seen this before, you can, well, kind of constructing using steps at t equals 0, t equals the period over 2, and t equals the period. Okay, so here we at t equals the period over 2, so we need to subtract 2 times the unit step to go to a negative value. Okay, so this is another way of writing this restriction of the function to this period 0 to t, right? If we now go to the Laplace domain, this is what you'll have. Okay, remember that the Laplace transform of a, well, unit step u of t is 1 over s, and that when you do time shifting, you'll have to multiply in the frequency domain, in the Laplace domain, by an exponential. Here it is an exponential of e to the minus period divided by 2s, and here it is e to the minus period times s, right? And what we have to do is use this Laplace transform, multiply by 1 over t, and replace s by jk omega 0, and omega 0 is 2 pi over t. Okay, and you will see that very quickly you obtain the same expressions as before, and indeed you see, using this expression here that we have obtained before, that ck is 0 for k even or 0, and that ck is given by this expression here for k odd. So without a surprise, the result is exactly the same. So what you have just seen is that you can use the Fourier series to decompose this square wave signal in terms of, well, the fundamental and, well, also harmonic components. And here the fundamental is given in green, and the harmonic components, third, fifth, and seventh harmonic component, are given respectively in red, purple, and orange, right? And if you add them, well, you get an approximation, and this is the approximation given in blue of the original square wave signal. And now what we're going to do is combine this with things that we've seen in the, well, previous section, okay, on the first order system and the Bode diagram. So here's the Bode diagram of a first order system, and what I've done over here is indicated with these vertical lines the frequencies that are corresponding in green to the fundamental component, and the frequencies that are associated with the harmonic components, in red the third harmonic components, and then in purple and orange the, well, fifth and seventh harmonic components. As the system is linear, you can kind of imagine that these fundamental and these harmonics components are going to go through the system separately, and then at the output you can add them. This is because of the linearity of the system. And you can see that these signals, they will be, well, attenuated and phase shifted. Here are the resulting outputs. Okay, so the green line is the fundamental component that goes through the first order system, and it's attenuated a bit, only approximately 1 dB, and there is a little bit of phase shift around 26 degrees. You can do the same for the harmonic components, the third, fifth, and seventh harmonic component, and when they go through the system, they are attenuated and phase shifted, right? In this case, for instance, let us take the fifth harmonic component. When it goes through the system, well, the gain is approximately minus 9 dBs and the phase shift minus 70 degrees. So what we can do now is sum these components, okay, fundamental and harmonic components that have gone through the system, and add the what will be the response. Okay, you obtain the response of this signal in blue. Okay, and you see that you obtain quite a good approximation of the actual response to the square wave. Okay, because this square wave is of course composed of 9th, 11th, 13th order components, but these frequency will be higher and they will get attenuated more and more, so that you don't see their effect in the response. So this slide is for your information only. What we have used as a Fourier series in this course is the following decomposition of f of t. It's a sum that goes from minus infinity to infinity of ck f of k, and f of k is the function, the corresponding function in the Fourier basis, right? And the reason why we have used this Fourier series is that it makes the link with the Laplace transform and the Fourier transform. As you can, or as you know, this can also be written as cos k omega 0 t plus j sine k omega 0 t, right? So there is this alternative Fourier series, which is called the Trigonometric Fourier series, and it decomposes a real value periodic function f of t of period t. Remember that omega 0 is 2 pi over t, as follows. So it's written directly as a sum, where k here ranges from 1 to infinity of, well, a term in cosine and a term in sine, and the coefficients that are of interest are ak and bk, and they are computed as follows. You can rewrite this expression here also, and it's done in the course, as a sum from 1 to infinity, so you can make the link between ak and bk with the Fourier coefficient ck, and this is actually done in the next slide, but I will not go into the details of that.